Hello everyone, welcome to Reactify Labs. In this video, we will talk about consistency models. Consistency models. What is consistency? Consistency means everyone should agree on one thing. Okay. As we have talked about before, in distributed systems, we have different nodes. Okay. Let's say we have different databases. If in one database we have some value of x as 5, then all the other databases should have the value of x as 5. This is consistency. Okay. It means everyone should be consistent. That's what literal definition of consistency is, and that's what it is. We don't have anything else in consistency. But what this video will focus on will be consistency models. Okay, so let's see what consistency models are. We'll start by defining consistency, and then we will move slowly to that. So, what is consistency first? Consistency is the agreement of all nodes consistency is the agreement of all nodes in a distributed system. All nodes in a distributed system should agree on a single up to date value for a piece of data. In the example that I had provided, that piece of data was X. Okay. Why we need consistency? Why? So ensures that consistency ensures that users and applications receive accurate and reliable information from database. Accurate and reliable information from the database, right? We need reliable information. For example, let's say we have two users, X and Y. X sends 100 rupees to Y. Okay. And before that, X has 100 rupees or $1,000, let's say $1,000 in his account. Y has $1,000 in his account. X sends $100 to Y. Okay. So this will be updated to 900. Y did not receive it, for example. Y's balance is still 1,000, right? Y did not receive it. So this is not consistency. Consistency means if a transaction happened between two entities, two people, two parties, then their state should be consistent with each other. In that case, what happens is, let's take another example. For X, it got deducted 100. Here it got credited 100. It failed to update. It's still showing 1,000. So if you see, X has discovered an infinite money glitch here, right? Infinite money glitch. X will see that no matter how many times he sends the money never reduces. So what X will do is X will just set up another bank account and just keep on sending money from his current account to the next bank account, because this amount never gets reduced. So that's why we need consistency. Everybody should see that, okay, if something has happened, that effect is getting reflected there. Okay. So we will talk about this in the models later. I was just explaining using this simple example that consistency should ensure that users and applications receive accurate and reliable info from database. Here, the info that the database gave was not reliable. The amount in X's account should not be 1,000, it should be 900. In Y, it should be 1,100, right? Then here, consistency models come into picture. Consistency models Consistency models define the rules. Consistency models define the rules governing how updates to a distributed system, how updates to a distributed system are propagated, and how different nodes in the system observe those updates. Observe those updates. It means if if one node got the update, if this node got the update, then what will be the state of this node and how does it propagate to other nodes, right? So this is what is defined by consistency models. Okay. There are two types of consistency models. One is strong consistency, and the second one is eventual consistency. So what strong consistency does is it ensures that all nodes in the system see the same data simultaneously. Okay. All nodes see same data simultaneously. It means every node should have only one copy of data. If in the account of X there is $1,000 and database has different replicas, then all the replicas should show these $1,000 only. Same data simultaneously. Okay. And there are some cases where we cannot afford the data to be different. Otherwise, that would not be a desirable system or a good system. Okay. In a strongly consistent system, I'll just erase it for now. If the system is strongly consistent, once a write operation is acknowledged, somebody does a write and it was successful. Once a write operation is acknowledged, any subsequent any reads after that write, any subsequent reads will return the value written by the most recent write. Whatever was written by the most recent write, only that will be returned, no matter where the query is happening. For example, if you are checking your bank account in US and it's showing you $1,000 and your database has different replicas, even if you are checking in Australia, this X should show 1,000 even though it is connecting to a different database server. So, and let's say somebody wrote something, you sent $100 to somebody. It means the next write which happened was $900. So anywhere in the world you should see $900, or anybody sees, they should see $900. Okay. So that's what strong consistency means. Uh, what guarantees strong consistency? Acid. Acid properties guarantee strong consistency. Okay. So that's why for financial systems, we prefer strong consistency, and that's why we use uh, databases which provide acid guarantees like SQL kind of databases. Okay. Great. Also, when a transaction is committed means again X to Y, 1,000, X sent 100, Y received 100, it's 900 now, it's 1100, and commit happened. Okay. Then when a transaction is committed, when a transaction is committed, all subsequent transactions after this, all subsequent transactions observe the effects of the committed transaction. Observe the effects of the committed transaction. What does this mean? It means once this transaction commit happened and the amount is now 900 and 1100, every transaction which starts after this commit should see these values of the amount in the account of X and Y. So it should observe the effects of the committed transaction. Okay. If the transaction was not committed, then it's not okay. Like, we don't need to worry. It can be the last committed value, which was 1000. But once the commit has happened, subsequent transactions would work on these values. Now, if this person has to send another $100, it will be deducted from 900 because this was the value written by the last committed transaction. Okay. So if we need these many facilities, then they will come with their own challenges. So what are the challenges with strong consistency? The challenges is latency. One is latency. Second is scalability. And third is availability. What do these mean? Achieving strong consistency requires synchronization and coordination. Okay. So let's say there are different database nodes. Okay. One is in US, one is in India, one is in Australia. Okay. All these databases have the same data. Everything has the value in the account of X, which is $1000. X has $1000, X has $1000. Now X was in US, X sent $100 to somebody. Now the value in X's account is 900, right? And X wants to do another transaction. But the problem here is, if X does another transaction and meanwhile before that these databases are not updated, the problem will be a glitch. Here it's 900, here it's 1000, and if subsequent transactions read these values like 900, 1000 and 1000, which will be wrong, right? So that's why we need to wait. We need to wait for this database to propagate the information to this database and this database, that you have to update it to 900 now. And by the time this update happens, by the time this propagation happens, this system may not be available for use. That's why the latency issue comes in. Means you cannot use it quickly. You have to wait until database updates everywhere, and only then you will be able to use it, which will obviously have a bad impact on your user experience because of latency, but it's good in terms of the scale at which these transactions happen, because you cannot bear the misplacement of even 1 rupee or $1. Okay, 1 cent also. So that's why the latency issue comes in. Scalability issue comes in because ensuring strong consistency in a distributed system like this, in this distributed system, will pose challenges in terms of scalability because of the number of nodes. As the number of nodes increases, then we will have to propagate to every node. Here another node, here another node. We have to propagate it to every other node, and making sure that the successful receipt of the information in all the nodes. Okay, that's where the scalability challenges come in. You cannot scale it too much and expect the latency to be low also. Next is availability. In scenarios where network partitions occur or nodes fail, ensuring strong consistency may lead to temporary unavailability. And as we have discussed in cap theorem, we can only achieve C or A because P is a must. We have to use P, so we can only use C and A. And if we here we have strong consistency, we have strong C, it means we are ready to compromise on A. We are ready to compromise on A, right? So the availability will be compromised here if we want to achieve strong consistency. The systems may be down for some time. the system may not respond to you as you would want, because system wants you to have strong consistency, and it's ready to compromise on the availability part. Okay, good. Now, next, let's talk about eventual consistency. Eventual consistency. What do? They allow for temporary inconsistencies between the nodes, between the nodes with the guarantee, that if given enough time, if you give them enough time and absence of further updates, then all replicas will converge to same state. Okay, it is what did it say? It said that we do not need strong consistency. We don't want the data to be updated as soon as it happened, but it will be updated eventually. Maybe in next 1 hour, 2 hours, it will be done. And we are willing to have that in those kinds of systems where the consistency is not very crucial. I'll give an example. It's favored where in distributed systems where we need high availability and partition tolerance. So we need high availability. We don't need consistency. Means people are not worried about whether they are getting fresh data or not. What they want is they want data, even if it is stale, even if it is old, but they want data. Okay, where would somebody want that, or why would anybody want bad data? We do. We would want it, and we want it every day. Let me give you an example. Instagram. The best example that I can think of, I have given it in my other videos also. It is a celebrity post. It is a celebrity post, and again, there are different database replicas: US, India, Australia. There is a celebrity called Ronaldo. Let's say Ronaldo made a post. It went viral. You are in US, you are seeing it has 100k likes. Somebody in India sees it has 102k likes. Somebody in Australia sees it has 105k likes. Okay. Does anybody care what the number of likes here is? Or does anybody complain that, okay, I am not seeing the same number of likes as my friend? No. So here, this database has not yet propagated the information to this database. This database has not propagated the information to this database. And similarly, it is possible that none of their numbers are correct because nobody communicated with the other one. So these are the cases where eventual consistency is desired. Means at the end, obviously the databases will communicate later. At that moment, the post went viral. It means the Instagram servers have to handle a lot of things, a lot of other things. How to send the post to all the followers, how to handle the comments, how to handle the shares that is happening on the post, how to handle the messages that are going to Ronaldo's account. So that's why they are deprioritizing the number of likes at the moment. And when the noise reduces, when the load reduces, when people sleep, when the post gets old, at that time the databases will start diverting the resources to its or utilizing the resources which were supposed to be with them but went on to some other um, problems. And then the likes will get updated. They will all communicate amongst each other, and the likes will eventually converge to the same state. Okay. So NoSQL databases like Cassandra, they use eventual consistency. Okay. Updates to different nodes may take time to propagate, but eventually all nodes will converge. Just remember the word in the eventual consistency, it's eventual. Eventually everything will happen. Everything will converge eventually, and that's why it is called eventual consistency. Okay. And then what are the challenges that come with eventual consistency? The challenges that come with eventual consistency are: one is temporary inconsistencies. Obviously, temporarily there will be inconsistencies, but that's not an issue. But that is a challenge. We have to accept that is a challenge. There will be read anomalies. One person is reading the number of likes different. One person is reading the number of likes different. These are read anomalies. Okay. Conflict resolution. This is actually a real problem. We know that temporary inconsistencies will be handled by eventual consistency. Eventually, these temporary inconsistencies will be resolved. Eventually, these read anomalies will be resolved. But how? The question comes here: conflict resolution. How are we going to resolve the conflict? How will we know who is the source of truth? How will we know that one database, when communicated with other database, the other database read the information sent by them? They actually received it. They processed it. They sent the acknowledgement. Everything. This is a very important thing to be handled here. Very important challenge. And there are different algorithms, different mechanisms for this, about which I'll talk in later videos. But right now, know that this is a very serious problem. Conflict resolution mechanism. Okay. Great. What are the different strategies for addressing challenges? Mostly this conflict resolution. The strategies are the different strategies are: one is version vectors, and there are other conflict resolution mechanisms, and I'll talk about these in later video, not in this video. Let's take some real world examples of different systems which follow eventual consistency and strong consistency. Okay. Examples. So for eventual consistency, we have something which I give the example for: social media feed. In social media platforms, eventual consistency allows for quick posting, quick updating of content across distributed servers. Users, it is possible that users don't see the post immediately, but after some point of time, they will see it. You will see that you might be able to see a post, but your friend is not, because the database has not updated yet, but it will get updated eventually. Similarly, for product catalogs, the product catalog, once the product gets updated or the added to the catalog, it's possible that you might not see it because your database might not have received the update yet, but you will receive eventually. Unless it's a that kind of product for which there is a huge line, huge crowd, huge fight, strong consistency is not desired. Now let's take the real world example of systems which have strong consistency. Financial transactions. Financial transactions, as I explained before. Another good example is reservation systems. Reservation systems. As soon as you book the reservation on flight or movie or train, your seats should be locked or your reservation should be locked. It means anybody who is doing the reservation after you should have that information that, okay, there is one person who has already done before me. Even if that difference is 1 second, that should be taken into account. And even if it's 1 millisecond, that should be taken into account. And that's why strong consistency is desired. Okay. There are some techniques for implementing consistencies. Let's just talk about them at a very high level. I'll make separate videos on that as well. So, techniques for techniques for implementing what? Strong consistency. For implementing strong consistency, one is two-phase commit and another is quorum based system. Quorum based system. Okay. And for eventual consistency, we have CRDTs, conflict free replicated data types, and we have also something called vector clocks. Also, actually, I think I forgot to mention one thing. This conflict resolution, this is an issue in strong consistency as well, not only in eventual consistency. So if you see here, when we say techniques for implementing strong consistency, it means for implementing, we have to resolve the conflicts, and we have to make sure that we have to know which node has the right database, which node is the source of truth. So that problem is there also, and we will solve it. There will be many more videos coming on how to uh, implement consistency, how to resolve conflicts. And with this, I'll end this video. I hope this explains a lot about consistency models, where each kind of consistency model is desired and where each is preferred and where you should use what. So that's it for this video. Thank you for watching. Please remember to like, share, and subscribe. I will see you in the next one.